videos are about my life and study. If you like my videos, please subscribe and hit the notification button. Thanks! Right and go! Hi, today we'll be proving that the fifth Fermat number is a constant number. Now this constant number is relatively large and it is equal to 2 to the 32nd power plus 1. Now its first prime factor is 641, which ranks quite large among the primes. Now, of course, if someone were as dumb to fully find the value of the fifth Fermat number, which is not quite a monumental task, and go through the primes one by one, he would surely take a few months, give or take a few weeks. Now, to find this value, then we obviously need to not just plain divide. And so we are going to use a method developed by Gauss called modular arithmetic. Now modular arithmetic basically is that it brings numbers into a specific interval. And if you have a given value, you can also think of it as A mod B as the same as A divided by B, and the remainder would be A mod B. And so therefore, we can use this idea to our advantage. First of all, if we write 641 as 2 to the fifth power plus 2 to the fourth power plus 5 to the fourth power, and also as 2 to the seventh power multiplied by 5 plus 1, then if we rewrite this equation, we can easily say that 2 to the seventh power multiplied by 5 is congruent to negative 1 modulo 641. Now, if the fourth power both sides of the equation, noting that negative 1 to the fourth power is 1, then we can write this equation as 2 to the fourth power, while 2 to the 28th power multiplied by 5 to the fourth power is congruent to 1 modulo 641. Now, of course, we can't just say that we're done, because if you take a look at this number, you'll see that clearly it has nothing to do with our value of 2 to the 32nd power. Now, if we take a look at our 641 is equal to at the top, then if we rewrite it, we can deduce that 5 to the fourth power is congruent to negative 2 to the fourth power, well, modulo 641. So if we bring it into our equation, we can write it as 2 to the 28th power multiplied by negative 2 to the fourth power is congruent to 1 modulo 641. Now, basic exponentation tells us that 2 to the 28th power multiplied by 2 to the fourth power is 2 to the 32nd power, which in this case is pretty close to what we need. But we have a negative sign to deal with. So first, if we put our negative sign in front, we can write it as negative 2 to the 32nd power is congruent to 1 modulo 641. Now, if we multiply both sides by negative 1, we effectively remove the minus sign or negative sign from the left side equation and add it to the right side of the equation. Now, if we just add 1 to both sides of our equation, we can get 2 to the second power plus 1 is congruent to 0, modulo 601. Now this proof definitely does not give you the value of our other product. But if you do the long division, it becomes clear easily. This proof actually got to tell you what one of its prime was. But if you try to prove that the 20th Fermat prime is composite, then of course it would take a very long time, since so many of these are most of these are prime checking algorithms that don't actually give you the factors of this number. And in case you wanted to know, all values of n from 5 to 32 have been proved to be composite, which technically means that the only Fermat primes we know are 3, 5, 17, 257, and 65,537. Now, this proof is very elegant, and of course Euler did not use this proof as he had to find out which factor it had. But in the end, the result is the same, and it disproved Fermat's theory or conjecture. That's all for today, and see you next time.